Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its advanced analytics solutions for oil and gas transport systems optimization. Oil supply chain optimization. The oil and gas supply chain is made up of 4 links: upstream, midstream, downstream and retail. The links are connected by multimodal transport networks. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The table, elaborated by IBM, shows a resume of the optimization solutions for oil and gas enterprises. The distribution chain of petroleum products begins in refineries and ends at the sites of consumption of different types of products. Optimization solutions in the transport chain of petroleum products can be classified by their hierarchy, strategic, tactics, and operating. Several of these applications will be discussed below. Oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of High Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detail the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. Oil transport systems optimization corresponds to a general model, common to all types of oil products, raw, refined, natural gas and biomass, which represents the process for a specific system, including particular equations when this is required. It considers 2 types of transport modes: pipes and multimodal vehicle, like vessels, barges, train tanks, and/or trucks tanks. The integrated transport system can be conceptualized as the junction of pipe and vehicle routes, which interconnect multiple terminals, which are the places where are connected the different installations. Each transport media is modeled independently. System connectivity is done through the terminal, a node, that corresponds to a point in the space in which at least 2 installations are interconnected, such as oil fields, plantations, oil refineries, biorefineries, port, consumer centers, and thermal plants. The table presents a summary of the mathematical models developed by HI for oil and gas transport optimization. Pipelines planning and scheduling. HI supports the planning and scheduling of oil products transportation through pipelines using 3 coordinated hierarchical models. Tactical planning determines the optimal volumes to be transferred in during the planning period, without considering the sequence of products in the pipelines. Batch scheduling determines the volumes and sequence of tenders to be transferred in during the planning period, considering the volumetric planning established at the previous level. And real-time optimization determines transfer speeds, discharge pressures, and pumping patterns, serial or parallel, at pumping stations, to meet batch scheduling established at the previous level. The optimization goal is to minimize operating costs throughout the entire planning and scheduling process. The real-time models includes nonlinear modeling that determine the amount of energy consumed based on the flow of products in the system. In aggregated models, when multiple types of products can be transported in the pipeline, the total transport time must be divided into the time used to transport each type of product at different transfer rates. To represent the flow of energy through the transport system, the following constraints should be considered. Energy conservation in the ducts and nodes of the system. Minimum pressure limits, or compression, at the outlet of the ducts, and pressure, or compression, minimum input to the ducts, depending on the type of connection between the operational area, node, and the duct. In the real-time model, a detailed hydraulic system is available in the pump operation model, for each type of pump in the pumping system, and each link in the pipeline, for each type of product, or crude. This ensures the feasibility of the results. The real-time model can handle differentiated electricity costs by time of day, or by load block, Using this way to take advantage of low rates, or low marginal costs, in periods of electricity low load. Natural gas supply chain optimization. Similarly, like oil, natural gas supply chain may be modeled as an optimization mathematical model to simulate the transportation and storage of natural gas. The diagram presents the natural gas supply chain. The main features are: natural gas is produced in gas wells, or as an associated product in oil and gas wells. The marketing of gas implies that it can be transported massively by means of gas pipelines, or in ships. For this it is required to turn it into liquid, in liquefaction plants, and later converted back into gas, in regasification plants. This usually happens at terminals in port. Transportation through pipelines requires gas compression stations, (Y). Finally, the gas is delivered to a market, usually segmented, in industrial, vehicular, residential and commercial, and thermoelectric plants. As integrated products, electricity and gas must be modeled together. As a basic energy, the natural gas is a raw material of electricity, and in turn, as useful energy, it is competition of electricity. The optimization model includes the following types of nodes. Production fields. Consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. Similarly, like oil and LNG, liquefied petroleum gas, LPG, distribution chain may be modeled as an optimization mathematical model. Liquefied petroleum gas distribution chain optimization. A mathematical models for distribution planning and propane gas containers gathering. It is aimed at supporting the weekly and daily programming and operational rescheduling of trucks dispatch. The modeling hypotheses are as follows. Fleet of vehicles consisting of multiple type of trucks and multiple type of LPG trailers. Trucks can be moved with or without trailers. A truck can tow some type of LPG trailer. LPG trailers can be dispatched with or without charge. Vehicles move between nodes, or terminals. In the nodes there may be demands that must be met, or purchases that enter LPG into the system, and LPG storage tanks may exist in the nodes. Similarly, like oil, natural gas supply chain may be modeled as a mathematical model to simulate the transportation of natural gas, that describes its processes of supply and demand. The optimization model includes the following types of nodes. Production fields. Consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. Vessel scheduling optimization supports the programming of collection and/or distribution operations of products via maritime ways, in tankers and barges. It considers restrictions for delivery and load time windows, distribution of capacities on ship, loading and unloading capacity at the docks, draft capacity of the spring, speed of movement of ships, tanker weight to draft ratio, and synchronization of filling, or emptying, of storage tanks. When it is necessary to make decisions about the displacement of the vessel, it is of fundamental importance the correct modeling of the consumption of energy, which has a nonlinear behavior, with respect to the engine speed of the vessel. This constraint can be included in the mathematical model, as well as the modeling of tidal movements when entering or leaving ports. It should be considered that from the point of view of fuel consumption, the efficiency of an engine is not linear, and is not given to the maximum of its power. Minimum cost RPMs are close to their maximum capacity, in figure 80%. From that point, as the speed of the vessel's engine moves away from this point, the amount of fuel consumed per unit of displacement increases. On the other hand, these curves change depending on the weight of the vessel. A real case of distribution of petroleum products by sea, with tidal restrictions, is the one that occurs in the planning of the distribution of products from the Talara refinery along the oil terminals in the Peruvian coast. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.